Okay, so today we're going to finish this lecture on search trees. So a quick refresher, this is a table that we have reached last time. So we have seen implementation of the dictionary abstract data type using many different data structures, and the best or the most promising that we have found was the binary search tree, which gives us a complexity of big of h, where h is the depth of the tree, which has values anything from log n to n. And basically, we said that it's promising because we might have a way of causing the tree depth to go near log n, and this is what we will see in this last part of the lecture. So the depth of the tree depends on the order in which we perform insertion. So if we have a dictionary of elements 1, 2, 3, 4, 5, I mean keys 1, 2, 3, 4, 5, and if we insert them in the order 1, 2, 3, 4, 5, then we get a tree which looks like that. This is a binary search tree that we obtain when we insert the keys from 1 to 5. However, if we insert 3 first, for example, and then 2, and then 1, and then 5, and then 4, then we get a tree which looks like this. So the depth obviously has changed from here to here, and the reason for the depth change is the order of inserting the element in the binary search tree. So the way we insert elements is going to control the depth and hence the complexity of the operations, because whenever basically the complexity of the operations is going to depend on the shape of the tree when the operation is performed. If the tree is looking like that, the operation is going to be efficient, because the maximum, for example, here is 2, but the maximum here is 4. So one way to look at how we are going to improve the efficiency of the binary search tree. We said binary search tree depth is between log n and n. So one way of solving this problem, one way is to control the order of insertion such that we always insert. What do we always insert, in your opinion? How do we control? How do we get a nicely balanced tree, in your opinion? What should be the order of insertions? Are you awake? So, who can answer that question? How do you think we can control? How do you think we can choose the elements so that we get a balanced, nice tree instead of this linked list? Well, we can use the techniques that we have seen in quicksort before. We can choose an element at random. Okay, so we have a dictionary of elements. Let's say with keys 1, 2, 3, 4, 5, and what we can do is choose one element at random. And for example, like we said in quicksort, we are not always going to pick the pivot which splits the sequence into 2 halves, but with time, each time we pick, on average, we are likely to pick a key, in this case a key which halves the sequence. So we can be lucky and and pick the key 3 to insert first, and so on and so forth. So we can use the same idea we have seen in quicksort in order to divide the sequence, in order to divide the dictionary, or to pick first the root of the tree to be the middle element, and each time we always pick an element which is going to have one of the two subtrees underneath it. So we're going to be lucky and pick an element here which is going to have this into two halves, and an element here which is going to have these two parts, this subtree into two parts, etc. So we can use a similar argument to quicksort. In this case, the depth is still between log n and n. However, it is very likely that it is going to be log n. So the depth is going to be log n with a high probability. Now the problem with this approach is that in sorting we have all the sequence in front of us. Okay, so in sorting we have all the sequence in front of us. So we can choose the pivot to be a random number from this sequence. Okay. However, in a dictionary, we don't always have all the elements in front of us. Okay, a dictionary is a data structure where all the elements are going to be added and removed in different times. It's not like a sorting problem. In a sorting problem, you want to sort a sequence, all the elements are in front of you, and you are going to sort it. In a dictionary, we don't have all the elements. For example, this dictionary could be the basis for implementing a database of customers. Now, we don't have all the customers in one day. More customers are coming tomorrow. Some of them are removed tomorrow. So the dictionary data structure does not hold all the possible elements that are going to be in a dictionary. If all the elements are here, yeah, we can pick at random elements and get some sort of a balanced search tree. But because the elements are not always there, we cannot pick at random. So the problem of applying the quicksort trick here, picking elements randomly, has two problems. One of them is that there is no guarantee. There is no guarantee that it's going to be that the depth is always going to be close to log n. It will be with a high probability, but not always. Okay. So in quicksort it was okay. High probability was okay. In a dictionary operation, we want something stronger than highly likely. We want something better than that. The reason for this is that these operations, they occur a lot. It's not like we do sorting once in a while. We always search, we always insert, we always delete. So we need something stronger than just the depth of the tree is going to be log n with a very high probability. No, we want something guaranteed. We want the depth of the tree to always be log n. That's the first thing. And second thing, the elements in the dictionary are not always present at the same time. Second thing, the elements in the dictionary are not always present at the same time. So we need a way such that we can control the depth of the tree without having all the elements in front of us. Okay, so this way we are going to use is called AVL trees. So there is a way to balance the binary search tree, and there are different strategies. And so once we apply one of these strategies to the binary search tree, we are going to get different trees depending on the strategy. So we can get AVL trees, red-black trees, 2-3 trees, splay trees, B+ trees, and so on. These are all balanced trees that you can get by modifying the binary search tree in different ways. In this course, we are going to look at AVL trees. Okay, so an AVL tree is a binary search tree which has a depth of log n in the worst case. Okay, so how do we guarantee that? This is what we are going to look at shortly. But you have to know that AVL trees are just one way of making the binary search tree self-balancing. Okay, So the binary search tree has a problem when it inserts element or deletes element. It becomes unbalanced. For example, either grows from the right or grows from the left. Now these self-balancing trees, when we remove an element, or add an element to the tree, we are going to make certain operations to maintain the ordering of the tree to be balanced. How do we do that? Let's look at it through an example. Okay, again, let's consider our dictionary of elements 1, 2, 3, 4, 5, 6. Okay, and let's say we are going to insert them in the order 1, 2, 3, 4, 5, 6. So if we are using a binary search tree, what we are going to get is basically 1, 2, 3, 4, etc. the way we have seen it. However, when we use AVL tree, this is what is going to happen. I'm going to draw in front of you what is going to happen in an AVL tree so that you get the general idea. And after that, I'm going to explain the steps one by one. So in an AVL tree, what happens, we perform the insertion like we used to do. So first the tree is empty. So then we put the first element 1. And then it comes to the second element. We put it to the right of 1, because this is how we do insertion. And then it comes to the third element, and we put it here as well. And then we say, this is not right, this is unbalanced. So we balance it, and we make it look like this. And this is still a binary search tree, because we still have this element, and this one is larger, and this one is smaller. And then we continue doing our insertions. So now we have this true, we add 4, and we say, well, this is still okay. And then we add 5, and then we say, no, this is no longer okay, it's not really balanced. So we try to balance it, and we make it look like this, for example. Okay, and then we add. Okay, and then we add 6, and then we say, no, this is not balanced, and we try to balance it by making 4 as the root, 3, and bringing this part under 3. So this is how it works in an AVL tree from a high level perspective. So we have a tree. We do insertions like we usually do in a binary search tree, and each time after each insertion we check, is the tree balanced or is it not balanced? If it is balanced, we don't do anything. If it is not balanced, we try to fix in a certain way. Okay, now we are going to see how we know that the tree is balanced or the tree is not balanced, and what is the exact mechanism of fixing a non-balanced tree and making it a balanced tree. So again, we start by node 1. So we put node 1 and we do the check. Is it balanced or is it not balanced? So what it means to be balanced. A tree is balanced if all the nodes are balanced. A tree is not balanced if at least one of the nodes is not balanced. Okay? So this is a tree and it has one node. So the tree is balanced if this node is balanced. Now, is this node balanced or not? How do we know that? We compute the depth of the tree, of the subtree to the right and the subtree to the left. So the subtree to the left and the subtree to the right, they have the same depth because both of them are null. Okay? The depth of this tree, obviously, the depth of the tree 1 is 0. We can also say the depth of the tree, which is null, is -1. We can conventionally say that. So this one has depth -1. This one has depth -1. They're both equal, so it's not a problem. When does it become a problem? It becomes a problem when the difference in the depth is is greater than when the absolute difference in the depth of the right tree and the depth of the left tree is greater than 1. Okay, this is when it becomes unbalanced, when the node becomes unbalanced. We will see that. So first, there is the node 1. It has a right tree and a left tree. The difference between the right and the left tree is 0. So this one is balanced. Now we add node 2. And then we compute the depth again for every node. Okay? So node 2, the difference in depth between the right and the left is 0. And the difference in depth for node 1, this one has depth 1, this one has depth this one has depth 0, because this subtree has depth 0, this subtree has depth -1, and the absolute difference of the two is 1. So this is a tree where this node has what we call a balance factor. This is the balance factor, okay? Balance factor. This has a balance factor of 0, and this has a balance factor of 1. None of them is greater than 1, and so the tree is still balanced. We don't do anything. Now we do insertions for 3. And we compute the depths again. So the depth here is 0, because both subtrees are null. The depth here is 1, because this subtree has depth 1, this sub 0, this subtree has depth -1. And this node, this tree has depth 1, and this one is -1, and this one is -1, and then the difference is 2. So now there is something wrong. This tree is not balanced, and it is not balanced at this node here, so we are going to balance it. How do we balance it? We perform a rotation. We are going to see the rules of the rotation in the slides. However, here what happens is, this node, which is not balanced, we need basically to bring it down here, down this node. Okay? So this becomes 2, 1, and 3. And this is still a binary search tree. The ordering of the keys is still maintained. And we compute the balance again. This is 0, this is 0, and this is 0 as well. Now we insert 4. So the balance factor in 4 is what? Can somebody answer? The balance factor of node 4 is 0, and 3 is, and 1 is, and 2 is. Well, let's use the absolute value. So the absolute value of the depth of right minus depth of left, or vice versa. So that's going to be 1. Okay, so this is still balanced. And now we do the new insertion. So we perform 5. Now what's going to happen now? This is 0. This is 1, this is 2, this is 0, and this is 2. Okay, so after adding this insertion, the first node where a balance, an unbalance occurred is this one. So this is the one we're going to fix. So we're going to fix that like we did before. So 4 is here, 3 to the left, and 5 is here, and then 2 and 1, they stay the same. And we compute again that's going to be 0, that's going to be 0, and that's going to be 0, that's going to be 0, and that's going to be 1. The tree, as you can see, has been balanced because all balance factor at all nodes are, none of them is actually greater than 1. Now let's add 6. Now what happens is that this becomes a 0, this is still 0, this is 1, this is 1, this is still 0, and 2 is 2, right? Because this subtree has depth 2, and this subtree has depth 0. 2 minus 0 is 2. Okay, so the node 2 is problematic, so this is the one we're going to fix. Again, we have to put this node, we have to put this node with its child underneath the node. Yes.
Why we put 2 in the top.
Right. So we said the balance factor is the absolute difference of the tree, of the depth of the left tree minus the depth of the right tree, or vice versa. Now, what is the depth of the left tree? The left tree has one node. We said the depth of the tree is the depth of the deepest node. This is a tree which has only one node, which is the root, and the depth of the root is 0, and hence the depth of the tree is 0. So its absolute value of 0 minus. Now, what is the depth of the right tree? Is 2. The deepest node has got 2 edges from the root of this tree, so it's 2. And I believe this is equal to 2. And this is the 2 that we have here. Right? Okay, and then we are going to balance this again. So this 4 is going to go to the top. 5, 6. This becomes a child of that. Whatever is the child of this node is going to become the right child of that node, and this is how it's fixed. Okay, I mean, can you check that everything is still okay? So 3 is to the right of 2. 3 is still to the right of 2. 1 is to the left of 2. 1 is still to the left of 2. 3 is to the left of 4. 3 is in the left of 4, and so on. These operations that I am performing here, they are called rotations, and there are four ways that we can do them. So the non-balanced node can be the non-balanced node can be something like that. So this is the non-balanced node, or it can be something like that. This is the non-balanced node, or it can be something like that. This is the non-balanced node, or it can be something like that. This is the non-balanced node. We call this case right, which is the one that we have seen in the example. Symmetric to it is this case, which is called left. This is called right because there is a right child, and this is called left because there is a left and left child. This is called right because there is a right and left child, and this is called the left because there is a left and then a right child. Okay, so we have seen this part, and very similar to it, there is this part. Okay, so we have built our dictionary by inserting in 1, 2, 3, 4, 5. We can see this way by inserting into 5, 4, 3, 2, 1, etc. And then there are these two cases. There is this, and there is that. Okay, so let's go back to the slides now. Okay, so binary search tree the binary search tree provides a depth of h for the dictionary operations, or a complexity of big of h for dictionary operations. And to improve it, we are going to upgrade for the dictionary operations, or a complexity of big of h for dictionary operations. And to improve it, we are going to upgrade our binary search tree into something more powerful, into a self-balancing binary search tree. And there are different ways of making the binary search tree self-balanced. One of them is by turning it into an AVL tree. Okay. Now, how do we turn it to an AVL tree? It's basically whenever we perform an insertion or whenever we perform a deletion, what we do is basically to compute the balance factors at all nodes. And if we find there is a node where the balance factor is the balance factor is greater than 1, we have defined the balance factor to be the absolute value of the difference between the depths of the subtrees. We can also define it as being just the difference. If we define it as being the absolute difference, then a node is unbalanced if the balance factor is greater than 1. If we don't use the absolute difference, then a node is unbalanced if the factor is greater than 1 or less than -1. So it depends on how you define it, right? So this is the essence of the AVL tree. After each insertion, each deletion, we are going to compute the balance factors. And if there is any node which is not balanced, we are going to perform what we call a rotation, like we saw in the example, in order to make it balanced, such that after the rotation is going to guarantee that all the nodes after the rotation are going to have a balance factor in the range -1, 0, 1. Okay, none of them is going to have 2 or -2. And rotations, they are performed like that. So this is the case that we have seen. So this is just an abstraction of the tree, and this is the node where the problem is occurring. This node has a balance factor of 2 or -2. So how do we rotate it? So this is the case right, and we said symmetric to it there is the case left, and this is the case right, and symmetric to it there is left. So we are going to see this and see this. The other two cases are just symmetric. Okay. So the first case we have seen was that. No. There is something not right. Okay, there is something not right. This is the right case, and this is the left case. So the case that we have seen is this one. So basically the problem is at this node, which has a balance factor greater than 1, okay, using the absolute value definition. So the way we fixed it was to put this node with the left child. This is a left subtree. We put this node underneath R, and this, whatever is underneath R, we are going R, and this, whatever is underneath R, we are going to put it to the right of this node. Okay, remember, we have seen something like 1, 2, and 3, and the way we did it was 2, 1, and 3. Okay, so what we did was take this node, which is 1, with its left subtree, which happens in this case to be a null pointer. Okay, we have put them to the left of 2, and whatever was to the right of to the left of 2, sorry, here, whatever was, we put it to the right of 1, and it's just an empty pointer in this case, an empty subtree, sorry, in this case. So this is how rotation is performed. This is the problematic node, so we are going to make it the left child of this node, and then the left child of that node, we are going to make it the right child of this node. It's very easy, and we perform that. So it's a simple pointer operation. We are just switching pointers, okay? Okay, and the complexity is going to be big of 1 for doing this rotation, because it has nothing to do with the size of the dictionary. This could be a huge subtree, this could be a huge subtree, this could be huge, this could be huge. However, all we need to do is to manipulate pointers, and this is going to happen in a constant time. Okay, so this is the first case that we have seen, and symmetric to it is the other case, which looks like that. Now, the other case, which is right-left, what we do, the tree is going to look like that. What we do is first transform it into a right-right case. Okay, so we have right-left. The first, we do it in 2 steps. The first step is to rotate it. We rotate it to make it look like a right-right case. And then the right-right case, we already know how to solve it. We solve it using this kind of rotation. Right? So the right-left case, we are going to rotate it to look like that. Now, how do we rotate it? We are going to bring first this part, or this node, which is like the last one. So this is the problematic node. So first we are going to rotate these 2 together. I mean, if you check the diagram carefully, we have maintained the binary search tree properties. R is bigger than RL. This is why it is to the right. B is bigger than R. It's still bigger than R. D is bigger than RL but smaller than R. D is bigger than RL but smaller than R. So we have maintained the properties of the binary search tree doing this first rotation. Again, this is a simple rotation, and it's going to cost us big O of 1. After we do this rotation, we apply the second rotation, which is another big O of 1. So applying or rotating the tree is going to cost us big O of 1. Now my question to you is, when we build the AVL tree, we are going to insert elements, and whenever we do insertion, and also applies for deletion, we are going to check the balance factors. If any one of them is greater than 1 or smaller than -1, is greater than 1 or smaller than -1, we are going to make a rotation to fix the tree. Now, so when do we perform rotation? Okay, so when do we perform rotation in an AVL tree? Do we always perform rotation? Are you boycotting the discussion in class or something? Are you completely clueless? I mean, you usually answer my questions. What's happening today? So my question is again, do we always perform rotation when we do an insertion in an AVL tree? Okay, so in which case do we perform rotation?
Unbalanced. If it is unbalanced tree,
How do we know it's unbalanced? How do we know it is unbalanced? Yeah, what's with the balance factor? You are clueless. Okay, again, the quiz is going to be on this lecture. I don't know what's going on now. An AVL tree, we perform insertion like in a binary search tree, and we always check the balance factors. So we put 1 and check the balance factors. If any one of them is, if the balance factor of any node is greater than 1 or less than -1, then the tree is unbalanced. So this one is good so far. We always update 0, 1. We put 3, and that's 0, 1, 2. Now there is a problem. Now in this case, we are going to balance the tree. So as you can see, we have done the first insertion, and we did not need to do any rotation. We have done the second insertion. So first, there is no tree. We perform the first insertion. No rotation is needed because the balance is okay. We perform the second rotation, the second insertion. We compute the balance factors. Nothing is needed. No rotation is needed. We perform the third insertion. Now one node has got a one node has got a bad balance, so we're gonna make a rotation now. Okay, so in this insertion there was no rotation. In this insertion there was no rotation. This insertion necessitates a rotation. Okay. So do we perform rotation when the balance factor of at least one node is greater than 1 or less than -1? Now the next question is, can we? So let's say we are going to build an AVL tree from a dictionary which has 1,000 nodes. Right? So we have a dictionary, it has 1,000 nodes, and we are going to build an AVL tree from this dictionary. Can the balance factor of any node be 3?
no.
Why?
Because we count the tree and balance it. When it's bigger than 2, we balance it, so it's never gonna be 3.
Yeah, thank you. That's right. So basically, the balance factor, if we see value 2, we are gonna rotate and we are gonna fix it. So we never see the number 3. If it's -2, we're gonna balance and make it 0 or -1, and we were never gonna see the number 3. So as soon as we see the number 2, we're gonna balance it. as soon as we see number 2, we're going to balance it. So it's never going to be number 3 or bigger. This means that, so this insertion has happened in a tree which is balanced. This insertion happened in a tree which is balanced. Once we put this insertion, actually, we have put this insertion in a tree which is balanced, but the insertion caused the tree to be unbalanced, but we balanced it at the end. So the next insertion, 4, is going to happen in a tree which is balanced. So each time the tree is unbalanced, we are going to balance it. So that next insertion or next deletion is always going to happen in a tree which is balanced. Okay? This means that every time we perform an insertion or a deletion, the tree is always going to be balanced. So the depth of the tree is always going to be log n. The tree is always balanced because no node has got a subtree and a left subtree which differ by more than 1 or minus 1 or less than minus 1. Okay? So this is why the AVL tree always has a log n depth. It's because after each insertion, after each deletion, we fix it so that the next time when we do insertion or deletion, it's already fixed. And this is why it's called self-balancing. It fixes itself after every insertion or deletion if necessary. Okay? Now, let's look more closely at the complexity of performing an insertion in AVL tree. Now, how much does it take? For example, let's say we are at this balanced tree. This is a balanced tree. Okay? So this is 0, 0, 0, 0, 0, 1, 1, 1. Okay, so this is a balanced AVL tree. And next time we are going to insert something here. This is going to need some balancing. Okay, so let's say we want to perform an insertion. So the first thing in an insertion, what we are going to do, we are going to go down the tree. In order to find thing in an insertion, what we are going to do, we are going to go down the tree. In order to find where we are going to put the element. Okay, so this takes how much in complexity? So this takes big O of log n. And then we are going to put the element right here, big O of 1. Now after that, what's going to happen, we are going to compute the balance factors. We compute the balance factor of this and compute the balance factor of the parent, and the parent of the parent and all the chain. Do we need to compute the balance factor of this node?
No.
So we only compute the balance factor of the nodes from here and up. How many nodes are there? Log n. So we need to perform this operation log n times. Computing the balance factor in itself is constant, okay? Because all you have to do is to compute to make a difference between the depth of this tree and the depth of that tree. And the depth of the tree, you can store it as a field in your record, okay? So computing the depth of a node is big O of 1. So it's big O of 1 times a depth of log n, so that's big O of log n. Okay, and then we have found the node which requires rotation. So now we perform rotation, and rotation is going to cost big O of 1. Yes, because we said it's a constant, it doesn't depend on the size of the tree, right? And after that, we are going to recompute the new balance factors. We can either do it at the end of each insertion or at the beginning of... It depends. Let's do it at the end of each insertion. So recomputing them is going to be log n. So as you can see, nothing here is larger than log n. So at the end, it's big O of log n. So if you have a dictionary with 1 million nodes, it doesn't take much to insert a new node. In the worst case, you're going down 20 steps doing 1 or 2 steps, going up 20 steps in the worst case. You don't always need to go up all the way, especially when recomputing the new data, and so on. So at the end, it's a million nodes, okay, but you could get away with about 60, 70 steps, just to insert a new element or delete a new element. So that's how the AVL tree is going to help us achieve very good complexity for the dictionary operation. So finally, this is our result now. We have this AVL tree, and this is the complexity that we get using it. So it's big O of log n for every one of them, because we have controlled the depth of the binary search tree to always be log n. Right. Now we are going to see a way how we can perform sorting quite easily using an AVL tree. If you remember from the last lecture, we have seen something about the in-order traversal of a binary search tree. Okay, we said if this is a binary search tree, the in-order traversal of the binary search tree, which costs big O of n, is going to give us the elements 1, 4, 5, 7, 10 in this order. We have seen a function called print in order, which is going to visit the elements of the tree recursively and costs big O of n, and each time it's going to print a key, and the next time prints the key which immediately comes after this key, i.e. the in-order successor, in-order successor, etc. So this is the in-order traversal. So as you can see, if we have our elements in an AVL tree, then we can sort them. We can sort them, put them in a new array, basically by visiting them using in-order traversal. Okay, so we have a dictionary. It has elements 5, 3, 4, 2, 1, for example. Okay, and we are going to use an AVL tree. So this is our dictionary. We are going to use an AVL tree. So we are going to build first an AVL tree. Now, what is the time complexity of building an AVL tree? So dictionary has n elements. So the size of the dictionary is n. And we want to build an AVL tree by performing insertion. So how much does it cost us to build an AVL tree from a dictionary of size n? Log n is the cost of one insertion. Yeah, it's n log n, because in order to build an AVL tree, we make one insertion. Worst case is log n. Well, obviously this one is big O of 1, but insertion is log n. Another insertion is log n. Another insertion, perhaps with balancing, is log n. So there are n insertions, each one costing log n. So it costs n log n to build an AVL tree. And then we do an in-order traversal of the AVL tree, and this is going to cost us how much? In-order traversal costs big O of n. Okay, so the total is big O of n log n plus big O of n. That's going to cost us how much? Yeah, big O of n log n. So instead of doing the in-order printing, what we are going to do, we are going to copy the elements instead of printing them, okay? So instead of printing them to the screen, we're just going to copy them. So we have the dictionary. So this is the AVL tree that we build in n log n. And the in-order traversal, like the print in order, is going to copy in order. So we will have an array. We need an array here. So this is the tree. This is an array. Whenever, and there is an index equals 1. For example, 1, 2, 3, 4, 5. When we visit this element, what we do is we say A of index equals A of index equals this element E1. Okay, and then we visit this element, and then we say, and then index plus plus. Okay, index plus plus. So this is how we're going to change. We have seen the procedure called print in order. Now we can call it copy in order, and the middle part, which is about printing the value, instead of printing it, we are going to copy it inside an array, and like this we will have the sorted dictionary. So dictionary started as a set of elements. Okay, we build an AVL tree from these elements, set of elements. Okay, we build an AVL tree from these elements, and then we visit them in order. Each time we copy them inside the array, and like this we are going to have a sorted dictionary inside this array. In terms of space requirement, we obviously need extra space. We need space for the AVL tree plus space for the array. So it's big of an extra space. Okay, so if you have an AVL tree, if you have a dictionary and you have an AVL tree, you have an AVL tree already, and if you need to sort the elements of the dictionary, you don't need to apply a sorting algorithm because you already have an AVL tree. All you have to do is to apply an in-order traversal in big O of n. Okay, so in big O of n we can get the elements sorted if we have a tree already. I mean, compare this to, you have a tree and you go and apply merge sort, and that's n log n and another n log n. Well, it's better to have just another big O of n because you already have the tree and you can use in-order traversal. And that's what I'm talking about here. So we have finished this lecture. So we have seen what is a dictionary. We have seen concrete data structures and how they implement the dictionary. And they are lacking in terms of efficiency. So we have seen binary search trees, and they showed promise. Finally, we have seen self-balancing trees, exactly AVL trees. And we have seen how they maintain their balance while keeping a depth at log n, and effectively giving us a big O of log n efficiency or time complexity for all dictionary operations, lookup, delete, and insert. And you can read more about that. This is the lecture that's going to happen in next week's quiz. I'm glad that you understand it very well because I heard lots of you talking. So we will take a 5-minute break. Well, 3-minute break. It's 10:42. We meet again at 10:45 for the next lecture.